So this is part 2 of lesson 2.4. Now we're going to be talking about the force, the normal force. Okay. So what I didn't emphasize in the beginning when I first taught forces was that a normal force can only exist when there's a surface. Okay. And the reason for this is the fact that the normal force is a contact force that occurs when an object is touching another object, right? So there does need to be some sort of contact. So if you've ever heard someone say, oh, a contact sport like basketball or football or soccer, that means that you are actually going to end up touching the other player at some point. It's a contact force, which means that there is touching involved, okay? So if there is not a surface that is being physically touched, then there is no normal force, okay? That is a huge idea. As we know, the normal force points upward on a free body diagram, and its opposite friend is the force of gravity. So it's equal and opposite the force of gravity on a horizontal surface. The next thing that I'm about to tell you, it might seem like, whoa, like you just blew my mind. But if we ignore the fact that the normal force and the force of gravity are in opposite directions, we can agree that they have the same magnitude. That means that whatever number that we say the normal force is, let's just say, for example, if we say the normal force is 7 newtons, that means that the force of gravity is also 7 newtons because they share the same magnitude, but they just point in opposite directions. So for the following thing that I'm about to show you, you need to ignore the fact that the normal force and the gravity force are pointing in opposite directions. So I'm saying that the normal force is equal to the gravity force, and the force of gravity is equal to the mass times the acceleration due to gravity. So that's a lot going on, all right? So we know that the normal force and the force of gravity are going to be the same magnitude. So whatever number is there representing it, it's going to be the same. So just as this says Fn equals Fg equals mg, I can also write it as Fg equals mg and as Fn equals mg, because we're saying that these two guys, Fg and Fn, are in fact equal to each other. So it doesn't really matter who is set to what, okay? This whole thing is all the same. They're all equal to each other, all right? So as we know, Fn represents the normal force. We use capital N to represent newtons for our unit of force. Our force of gravity is represented again with the units of newtons, capital N. M is representing mass. We only use kilograms in physics. G represents the acceleration due to gravity, which is meters per second squared. So G is the same thing as me saying lowercase a, which stands for acceleration. However, G is specific because it belongs to a planet. So our planet's acceleration due to gravity, as we know, is 9.81 meters per second squared, but on the moon, it's 1.66 meters per second squared, okay? So now let's do an example together. So if we neglect air resistance, and neglect just means we ignore it, so we just say, ooh, it's not even there, can an object in free fall experience a normal force? So if we remember free fall, that is when an object is released and the only force acting on it is, in fact, gravity, okay? So free fall begins the moment it is released, right? So like, let's say I was holding a pen. It is not in free fall yet when it is still in my hand, okay? It is not in free fall when that pen hits the ground. When it touches the ground, it is not in free fall. So that means that free fall is when it is airborne. So the moment it is released to the moment before it hits the ground. That is what it means for an object to be in free fall. So again, this question is saying if we neglect air resistance. So if we don't assume that it's involved, can there be a normal force? Well, we know the normal force to be a contact force. That means it has to be touching another object or another surface. So no, you would not be experiencing a normal force if you are in free fall, okay? So no. Because a normal force requires there to be contact with another surface, and that's not happening here. Even if we add in air resistance, right, and I could draw a free body diagram on this rock, we know that the force of gravity always points down. If my force of gravity is pointing down, now that we are accepting that air resistance does exist, we're going to put it in our free body diagram. Air resistance will be the opposite force pointing up, okay? the force of air resistance is not equivalent to a normal force. They are not the same thing. A normal force requires contact between two objects or two surfaces, excuse me. If you do not have that going on, then no, you may not have a normal force, okay? So the big idea here is if there is no contact between surfaces, there is no normal force, all right? So that box is kind of just lingering over the table. There is no normal force going on yet, but until that box actually touches the table, then yes, there is now a normal force. So now we're going to move on to the scenario. So I want you to think about yourself driving down the road in the middle of a desert, and all of a sudden your car starts making these weird noises, right? The car starts to slow down on its own, and then it comes to a stop. However, there's a sign saying that there's a gas station a mile away, and you don't want to leave your car in the desert, right? So you decide, let me just try to start pushing it. So I want you to describe how the car starts moving involving the force applied and the frictional force. And if you were in class with me, you saw that I was putting students on chairs and doing something to them. So I would have them sit on the chair and I would push them to act as like the car scenario. Okay? So if I get out of my car and I go to push it, let's say I drive uh like a Toyota Camry, or let's say I drive a Mustang, right? I have this nice Mustang and all of a sudden it just stopped working. And I go to push it. I'm not going to start rolling it right away, even though I pushed it. Okay, so I'm going to be like, wow, like I actually got to put in some work. I have to apply a very large force to start moving it, right? So in the beginning, I have to apply a huge force in the beginning to get it to start moving. But then once it's moving already, the amount of force that I have to apply doesn't feel that bad anymore. It's not, I'm like, wow, I'm not feeling as fatigued. So what I'm trying to say is that the force applied in the beginning has to be bigger, right? So this needs to be big in the beginning. However, once it starts moving, it's no longer a problem. All right, so we're going to move on to the next slide. We'll keep that idea in the back of your head. And then we'll move on to the next slide. It'll all start to shift into place.